Hi friends, today I am giving a lecture on single source shortest path problem in dynamic programming. So dynamic programming is one of the algorithm design technique. So this technique is used for solving optimization problems. So here dynamic programming is mainly used for finding optimal solutions to a given problem. So it can take many number of decisions. So each and every decision should be optimal. So we have to find out the optimal solution for the given problem using dynamic programming. So here single source shortest path problem is there in greedy method and also in dynamic programming. So what is the difference between single source shortest path problem in greedy method and single source shortest path problem in dynamic programming? So in greedy method we have to use one algorithm called Dijkstra's algorithm for finding out the single source shortest path. We have to find out the shortest path from source vertex to remaining all the vertices of the given graph. So by using Dijkstra's algorithm, we have to find out the shortest distance between source vertex to remaining all the vertices of the given graph if the given edge weights are positive. If the given edge weights are negative, so the Dijkstra's algorithm may or may not produce the shortest path between source vertex to remaining all the vertices of the given graph. So this is the main drawback in a single source shortest path problem in greedy method. So if the given graph contains positive edge weights, so then Dijkstra's algorithm will work and find out the shortest path between source vertex to remaining all the vertices of the given graph. If the given graph contains negative edge weight, so the Dijkstra's algorithm may or may not produce the shortest path from source vertex to remaining all the vertices of the given graph. So to overcome this disadvantage, we have to use another algorithm in dynamic programming. That algorithm is called as Bellman-Ford algorithm. So Bellman-Ford algorithm will work if the graph contains the negative edge weights. So Bellman-Ford algorithm is used for finding out the shortest path from source vertex to remaining all the vertices of the given graph if the given graph contains negative edge weights. So by using this algorithm, we have to find out the minimal shortest distance from source vertex to remaining all the vertices of the given graph. So here we have to use one property called relaxation property. So the same property can also be used in greedy method, single source shortest path problem in greedy method. Once again I am telling what is relaxation. So relaxation property is nothing but, suppose there are three vertices are there. So this is the source vertex and this is the destination vertex. So three vertices, vertex 1, vertex 2, vertex 3. Suppose vertex 2 can be treated as U, vertex 3 can be treated as B, vertex 1 can be treated as source. So what is the distance between vertex 1 and vertex 2? That is 3. What is the distance between vertex 2 and vertex 3? That is 4. Okay, now dist of u. So what is the meaning of dist of u or d of u or d of u? So what is the meaning of this one? The distance from source vertex to destination vertex u. So here u is equal to vertex 2. So the distance from source vertex 1 to destination vertex 2. So d of u is equal to 3. Okay, next. What is the d of v? So d of v is nothing but distance from source vertex to destination vertex v by using the direct edge connection. So here source vertex is 1, destination vertex is 3. So there is no direct edge connection between 1 and 3. So then distance of v is equal to, can be treated as infinity. Distance of v is equal to infinity. Distance of u is nothing but 3. Okay. Now what is the relaxation property? So here u is equal, distance of u is equal to 3. Distance of v is equal to infinity. So the relaxation property is if d of u plus c of u comma v less than d of v. Here d of u is nothing but 3 plus c of u comma v. U comma v is an edge. What is the cost of u comma v edge? That is 4. So 3 plus 4. So less than d of v. D of v is nothing but infinity. So infinity. So that is 3 plus 4, 7. 7 less than infinity. So condition true. So then d of v is equal to d of u plus c of u comma v. Here d of u is 3 plus c of u comma v is 4. 3 plus 4, that is 7. So d of v is equal to 7. So infinity can be replaced as 7. D of v is equal to d of u plus c of u comma v. So 3 plus 4, that is 7. So then infinity can be replaced by 7. So this is the relaxation property. So this relaxation property is already used in single source shortest path problem in greedy method. So the same property can also used in single source shortest path problem in dynamic programming also. So how many number of edges to be relaxed? How many times we have to relax? That is n minus 1 times. Okay. How many times the edges to be relaxed is nothing but n minus 1 times. Here n is nothing but number of vertices in the given graph. Suppose, so if the graph contains 5 vertices, so how many times we have to relax all the edges is n minus 1. That is 5 minus 1, that is equal to 4. So 4 times we have to relax each and every edge in the given graph. Next, what is the time complexity of a single source shortest path problem in dynamic programming? So here big O of E into V minus 1. So here is nothing but E is nothing but number of edges in the given graph. Okay, how many times all the edges to be relaxed? That is n minus 1 times to be relaxed. Here n is nothing but number of vertices in the given graph. It can be treated as mod v. Mod v is nothing but number of vertices in the given graph. So here n into n, suppose capital E is equal to n. So n into n minus 1. So here v minus 1 is nothing but n minus 1. N into n minus 1, that is n square minus n. So in this one, highest polynomial is n square. So that is big O of n square. Suppose if the given graph is complete graph, so then the time complexity is big O of mod E. Mod E is equal to number of edges in the given graph is n into n minus 1 by 2. So next, how many times it is relaxed? How many times it is relaxed? N minus 1 times to be relaxed. So that is n minus 1 into n into n minus 1 by 2. So that is highest polynomial is big O of n cube. Okay. So if the graph is a complete graph, the given graph is a complete graph, then what is the time complexity? Is nothing but big O of mod E into n minus 1. Mod E is nothing but number of edges in the given graph. How many times all the edges to be relaxed? N minus 1 times all the edges to be relaxed. That is n minus 1 into mod E is nothing but number of edges in the complete graph is n into n minus 1 by 2. So that is equal to highest polynomial is big O of n cube. Next, what is the disadvantage of Bellman-Ford algorithm? So suppose if the given graph contains a negative weight cycle, so then the Bellman-Ford algorithm does not work to find out the shortest path between source vertex to remaining all the vertices of the given graph. Okay, if the given graph contains a positive weight cycle, so then Bellman-Ford algorithm will work and find out the shortest path between every pair of vertices. So if the given graph contains negative edge weights, so then we have to use Bellman-Ford algorithm. So Bellman-Ford algorithm will not work. The total weight of the cycle is negative. So then it cannot be used for solving, find out the shortest path from source vertex to remaining all the vertices of the given graph. Suppose we consider the given graph. So if in the given graph there is a cycle is there, that cycle is so 2 to 4, 4 to 3, 3 to 2, 2 to 4, 4 to 3, 3 to 2. So the total weight of the cycle is total weight of the cycle is so 5 plus 3 minus 10. So that is equal to minus 2. So the total weight of the cycle is negative. So then Bellman-Ford algorithm cannot be used for this graph to find out the shortest path from source vertex to remaining all the vertices of the given graph. Suppose if the cycle contains the total weight of the cycle is positive, then we have to use the Bellman-Ford algorithm for finding out the shortest path from source vertex to remaining all the vertices of the given graph. Okay, so the total weight of the cycle is negative, so then Bellman-Ford algorithm cannot be used. This is the drawback of the Bellman-Ford algorithm. Next, so suppose we want to find out the shortest path from source vertex to remaining all the vertices of the given graph, we have to use this formula. Before going to this formula, first dist power L of u. So what is the meaning of this one? So here distance from source vertex to destination vertex u under the constraint that this path contains L at most L number of edges. So suppose, so this is source vertex, so this is destination vertex u. Okay, so that the shortest path from source vertex to destination vertex u under the constraint that this shortest path contains at most L edges. At most L edges. That means between vertex V and vertex U, there is a shortest path is there. So to travel from source vertex V to destination vertex U, we want to travel through compulsory L number of at most L number of edges. So this is the point, meaning of this point. So DISTL of U be the length of the shortest path from source vertex. Source vertex is V to destination vertex is U under the constraint that this shortest path contains at most L number of edges. Between vertex V and vertex U, there are L number of edges are there. So we have to travel through L number of edges to reach the destination vertex U from source vertex V. Next, DIST power 1 of U is nothing but, so we are starting from source vertex V and reach the destination vertex U by traveling through only one edge. Here one is nothing but one edge. So that is nothing but cost of V comma U, because so vertex U and vertex V and vertex U are there. Vertex V and vertex U are there. It contains a single edge. Only single edge is there. What is the cost of the edge? That is cost of V comma U. Okay. Next. Finally, our goal is to find DIST n minus 1 of U. So why we have to use here n minus 1? So here we have to relax n minus 1 times of all the edges in the given graph. Here we have to relax n minus 1 times of capital E. E is nothing but number of edges in the given graph. We have to relax n minus 1 times of all the edges in the given graph. Okay, we have to relax n minus 1 edges. So then we have to find out the shortest path from source vertex V to destination vertex U. N minus 1 times of edges mod E. Okay. Finally, the formula is DIST power K is of U is equal to minimum of DIST K minus 1 of U, comma, minimum of DIST K minus 1 of I plus cost of I, comma, U. So here, what is the meaning of this one? So we have to find out the shortest path from source vertex V to destination vertex U. This shortest path contains at most K number of edges. Okay. So then minimum of DIST K minus 1 of U, comma, minimum of DIST K minus 1 of I plus cost of I, comma, U. Okay. Here U is the destination vertex. Before going to the destination vertex U, so one edge before U, what is the vertex is there? That vertex can be treated as I. So I is nothing but, suppose we can take the vertex I. What is the next immediate vertex? That is U. Okay. So minimum of DIST of K minus 1 of I, distance from source vertex V to destination vertex I plus cost of I comma U. Okay, so this value we have to find out, this value we have to find out. Among them, which is the minimum, that is the distance from source vertex to destination vertex U. Between them, there are at most k number of edges are there. So by using this formula, we have to find out the shortest distance from source vertex to remaining all the vertices of the given graph. Next, we go for example problem.